Hey everyone! Welcome back to Imtech. Today we're diving deep into one of the most fundamental data structures in programming: arrays. Here's what we'll be covering in this complete guide to arrays. What are arrays? Declaration and initialization. Accessing elements. Common operations. Types of arrays. Time complexity. Common search algorithms. Memory visualization. Real-world applications. And best practices. Let's start with the basics. What exactly are arrays? Think of an array like a row of school lockers. Each locker holds one item, and each one is labeled with a number, called an index. This makes it easy to access any locker quickly, just by using its number. Now let's break down what makes an array. An array. First, arrays have a fixed size. Once declared, their length can't change. Second, all elements must be of the same data type, like all integers, or all strings. Third, you access elements by index, which makes them very fast for retrieval. And finally, the data is stored in contiguous memory locations, meaning it's all laid out next to each other in memory. One important thing to remember: arrays use zero-based indexing. That means the first element is at index 0, not 1. Now let's explore how arrays are declared and initialized in different programming languages. We'll look at JavaScript, Python, and Java, and see how each handles arrays in their own style. Starting with JavaScript. Method 1 is the array literal. It's the most common and readable approach. You define values inside square brackets. Method 2 uses the array constructor to create an array. This is especially useful when values are dynamic or built programmatically. Method 3 creates an empty array with a fixed size, but without assigning any values yet. The array will contain 5 empty slots. Now let's move to Python, where arrays are typically implemented using lists. Method 1 uses square brackets to directly create a list of numbers. Method 2 uses the list constructor. It converts another iterable like a tuple or another list into a new list object. And method 3 uses list comprehension, a powerful Python feature to generate lists dynamically. Here, we're creating a list of squares from 0 to 4. Finally, let's look at Java. In method 1, you declare and initialize an array in a single step using curly braces. Method 2 separates the declaration and initialization. You create a string array of size 3, then assign values to each index individually. In method 3, you're declaring a double array with a fixed size of 10 using the new keyword. All values are automatically initialized to 0 by default. One of the most important operations when working with arrays is accessing elements. Arrays store data in an index structure, meaning each item has a specific position or index. Let's look at an example. Here's an array named colors containing 4 color names: red, green, blue, and yellow. Each color is stored at a specific index starting from 0. To access an element, use the array name followed by square brackets and the index. For example, colors 0 refers to the first element, which is red. If you want the third element, use colors 2. Remember, arrays start counting from 0, not 1. Colors 2 gives us blue. Colors 3 gives us the fourth element, yellow. And finally, colors 1 refers to green. But here's a warning. Always make sure the index you use actually exists in the array. Trying to access an index that's out of range will result in an error. For example, if we try colors at index 10, it throws an undefined or out-of-bounds error, because the array only contains 4 items. Now that we understand how arrays are declared, let's dive into some of the most commonly used array operations. We'll cover how to access elements, add elements to the front or back, and how to remove elements from either end of the array. Let's begin with accessing an element. Arrays use index-based access. This means that each value in the array has a numeric position, starting from 0. For example, array 3 retrieves the fourth element in the array, because indexing starts at 0. This operation is incredibly fast, taking constant time, also known as O of 1. The push operation adds a new element to the end of the array. Think of it like adding a book to the end of a shelf. The new element simply slots in at the next available index. This is also a constant time operation. Very efficient. Unshift adds an element to the beginning of the array. Unlike push, this requires all the existing elements to move one step to the right. It's more expensive than push because it shifts every item. Pop is used to remove the last element from an array. It's like removing the last book from a shelf. The operation is quick, efficient, and returns the value that was removed. Finally, the shift operation removes the first element from the array. Every remaining element then shifts one place to the left. Like unshift, this is a linear time operation and more expensive than pop. And that wraps up our guide to basic array operations. These are the building blocks of so many algorithms and data structures. So getting comfortable with them is essential. Arrays come in different forms, each with its own strengths and use cases. Let's explore the most common types of arrays, starting with static versus dynamic arrays. First, let's compare static and dynamic arrays. A static array has a fixed size. That means when it's created, you must define how many elements it can hold. It is memory efficient because the system allocates only the space needed. But the downside is, you can't grow or shrink it later. A dynamic array starts with a few elements, but it can grow over time. It's more flexible and is used in most real-world applications where the size of the data isn't known in advance. Languages like Python and JavaScript use dynamic arrays behind the scenes. And here's the key benefit. When more space is needed, new elements can be added to the array dynamically. Now let's talk about multi-dimensional arrays. These are arrays where each element is itself an array. A two-dimensional array, also called a matrix, is like a grid of rows and columns. It's commonly used in games, image processing, and scientific computing. If we want to access a specific element, we use two indices. For example, matrix 1, 2 means go to the second row and third column. And yes, we still start counting from 0. When we talk about how fast or efficient an algorithm is, we use something called time complexity. It describes how the runtime of an operation grows as the size of the input increases. In the context of arrays, different operations have different time complexities depending on how much work they require. Here's a breakdown of the most common array operations and how they scale. Accessing an array element by its index is O of 1 because it's like looking directly into a box. Using its label, instant and efficient. Searching through an unsorted array is O of n because you might need to check every single element before finding what you need. If the array is sorted, you can use binary search, reducing the time to O of log n by cutting the search space in half each time. Adding an element to the end is O of 1, assuming there is enough space, because it simply goes at the next available spot. But inserting at the beginning is O of n, because you have to move all existing elements to make room for the new one. Deleting the last element is also O of 1. You just remove the last item with no shifting involved. However, deleting the first element is O of n because all other elements must shift one place to fill the gap. Here's a quick visual reference of the most common time complexities. O of 1 is known as constant time. O of log n is logarithmic time. And O of n is linear time. These are the big O notations you will encounter most when working with arrays. Now that we understand what arrays are, let's look at how we can search through them. In programming, searching is a common task, whether you're checking if a value exists or locating its position in the array. Two of the most popular search algorithms used in arrays are linear search and binary search. Let's start with linear search. It's the simplest search algorithm and works on both sorted and unsorted arrays. It checks each element one by one from the beginning of the array until it finds the target value. Or reaches the end? It's easy to implement but not very efficient for large datasets. Here we have an array of values: 3, 7, 1, 9, 5, 2, 8. We're going to search for the value 5. Checking index 0, value 3. Not a match, moving to the next element. Checking index 1. Value 7. Not a match, moving to the next element. Checking index 2. Value 1. Not a match, moving to the next element. Checking index 3. Value 9. Not a match, moving to the next element. Checking index 4. Value 5. Found the value 5 at index 4. Linear search is reliable and easy to use, but it's not the fastest when dealing with long lists. For that, we need something smarter, like binary search. Next, let's explore binary search. One of the most efficient search algorithms, but there's one rule. The array must be sorted. Binary search divides the array into halves and checks the middle element on each step, based on whether the target is smaller or greater than the middle value. It eliminates half of the remaining elements. Here's our sorted array: 1, 3, 5, 7, 9, 11, 13. We're searching for the value 13. Step 1. We're checking the middle element at index 3, which is 7. Since 7 is less than 13, we search the right half. Step 2. We're checking the middle element at index 5, which is 11. Since 11 is less than 13, we search the right half. Step 3. We're checking the middle element at index 6, which is 13. It's a match. We've found our target. Binary search is fast, taking only O of log n steps. But remember, it only works on sorted arrays. Arrays are fundamental data structures in programming. But how do they actually exist in memory? In this visualization, we'll explore the physical representation of arrays at the memory level. We'll cover 4 key aspects: memory fundamentals, address calculation, CPU cache behavior, and multi-dimensional array layouts. Let's start with how computer memory works fundamentally. Memory is a linear sequence of addressable bytes, like a giant street where each house has a unique address. Here we see 12 memory blocks, each representing 4 bytes, typical for 32-bit integers. The addresses increment sequentially from 0 by 1000 to 0 by 102C. Now we're storing an array of 5 integers: 42, 17, 89, 33, and 76. See how they occupy consecutive memory locations. This contiguous allocation is why arrays have O of 1 random access time. Different data types occupy different amounts of memory. A char needs 1 byte, an int typically 4 bytes, and a double 8 bytes. This directly affects how many array elements fit in a cache line. The magic behind array indexing is this address calculation formula: base address plus index times element size. Here's a concrete example array with values 10 through 50. Notice how each element's address increases by exactly 4 bytes from the previous one. Let's break down the address calculation for element 2 step by step. Start with base address 0 by 2000. Multiply index 2 by element size 4 bytes to get 8. Then add them to get 0 by 2008. Modern CPUs don't access memory directly. They use cache lines, typically 64 bytes wide. When you request one array element, the CPU loads the entire cache line containing that element. Here's a cache line holding 16 integers. The green portion shows what gets loaded on the first access, typically an aligned block of memory. Sequential access is cache-friendly, as we scan elements 0 through 7. Each subsequent element is already in the cache line loaded previously. This produces predictable, fast memory access. Now watch random access. Jumping between non-adjacent elements forces the CPU to keep loading new cache lines. Each jump potentially causes a cache miss, slowing down your program by 100x or more. The performance difference is dramatic. Sequential access keeps data in fast cache memory, while random access triggers expensive memory fetches. This is why optimizing memory access patterns often matters more than reducing operation counts. Multi-dimensional arrays introduce new considerations. While we visualize them as grids, memory remains one-dimensional. The mapping strategy affects performance dramatically. Here's a 3x4 matrix in its logical form. The double indexing suggests 2 dimensions, but physically it must be linearized. Row major order, used by C and most languages, stores each row contiguously. Our first row, 1, 2, 3, 4, comes first, then 5, 6, 7, 8, and finally 9, 10, 11, 12. The address formula accounts for both dimensions. The row major address formula first calculates the linear index by multiplying the row number by columns per row, then adding the column offset. Multiplying by element size gives the byte offset from base address. 4, 1, 2. This becomes base plus 24 bytes. Arrays aren't just a computer science concept. They're used in real-life applications across many fields. From image processing to gaming, data analysis, and even building web apps. Let's begin with image processing. Images are made of pixels, and each pixel holds color information using an array of 3 values: red, green, and blue. Here, we see a 3x3 pixel grid, each cell represented by an array of RGB values. Using a 2-dimensional array, we can efficiently store and manipulate image data. Arrays are also critical in game development. Let's take a look at a tic-tac-toe board. The game board is a 3x3 2-dimensional array, storing each move as a value. It's easy to check for winning conditions like a diagonal match using array indices. Arrays are also fundamental to data analysis. Let's look at a bar chart showing monthly sales. We store sales values in a 1-dimensional array. Then we use functions like reduce to calculate the total, average, and growth. Arrays make it possible to process large datasets quickly and flexibly. This red line shows the average sales across all months. Arrays are the foundation for analytics in finance, marketing, and beyond. Finally, let's talk about arrays in web development. In an online store, shopping cart items are often stored in arrays. Each cart item is an object stored inside an array. The system uses reduce to calculate the total. Arrays make shopping cart management efficient and scalable. We can easily add new items using the push method. Arrays keep the cart dynamic, allowing for real-time updates on user actions. As we wrap up our journey through arrays, let's talk about best practices. These are simple habits that can make your code safer, cleaner, and more efficient. Now let's explore. Always check bounds. Accessing arrays without checking bounds is a common source of bugs. Here's a bad example. No checks, just direct access. It can crash if the index is invalid. The better version checks whether the index is within bounds before accessing the array. Now let's explore. Use descriptive names. Descriptive variable names are key to readable and maintainable code. Letters like A and B don't say what the data means. But clear names like userids and student grades make the code self-documenting. Now let's explore. Consider memory usage. Arrays consume memory. The larger the array, the more memory is used. This small array is memory-friendly. But large arrays, especially with millions of items, can use significant memory. Always consider the memory impact of your array operations. Now let's explore. Use modern methods. Modern JavaScript provides clean and powerful array methods like map, filter, and reduce. Older code uses loops, which are harder to read and maintain. Newer methods are more readable and often more efficient. Now let's explore. Handle edge cases. Handling edge cases protects your code from crashing and makes it more robust. Start by checking if the array exists. Then check if it's empty. If elements are null or undefined, handle them. Finally, safely process your data. Congratulations! You've now mastered one of computer science's fundamental building blocks. Let's crystallize what you've learned about arrays into these core concepts. Arrays are homogeneous collections. Their zero-index nature affects how we access elements. You'll encounter both static and dynamic implementations. Remember that different operations have varying time costs. These concepts power countless real-world systems. Always initialize properly and validate indices. Having mastered arrays, let's expand our knowledge to linked lists and beyond. This is just the beginning. Every data structure tells a story about how information connects. Thanks for watching. Be sure to like and subscribe.